Very good morning all. So myself Dr. Avinash K, Assistant Professor, Department of Chemistry, ATM College of Engineering, Mysuru. Today we are going to discuss on the determination of pKa value of a weak acid by using pH meter. It's one of the experiment which comes under the Applied Chemistry Lab for all streams provided by VTU. So, first thing, what do you mean by a weak acid? When you say weak, it means a partial dissociation in its solution. When you add an acid to its solution, it undergoes a partial dissociation, hence it is called as weak acid. So, we cannot measure the pH of the weak acid as the dissociation will be partial, means it will be incomplete. Hence, we cannot measure the pH. Measuring the pH is of no use in this case. So, what we do, we are going to measure the dissociation constant. The power, or what we call as potential of the dissociation constant of this weak acid will be measured. So, pKa is the negative logarithm of the weak acid for base 10. So, this is the dissociation constant. pKa is equal to negative logarithm of Ka. For this determination, we use a pH meter. Usually, a basic pH meter comprises of the following things. A pH electrode system made up of a glass electrode, and along with that, there will be a silver chloride reference electrode. So, it will be combined with the mercury chloride reference electrode, so that it becomes a combined glass electrode. Along with that, we need a pH meter. This pH electrode will be immersed in a test solution and will be connected to the pH meter. The pH is varied by the addition of titrant. In case if we take a weak acid, then we have to titrate this with a strong or weak base, so that we are going to see the change in the pH. Here in this experiment, we are going to titrate a weak acid with a strong base. So the following are the instruments what we are going to use: a standard flask to prepare the standard solution of sodium hydroxide, a microburette. We are not going to use a normal burette here, we are going to use a microburette, and a micropipette, and we are going to use a beaker, we are going to use the stirrer. No need of this graduation flask here. Further, we need a sodium hydroxide solution to prepare the standard solution, and we are going to have the mixture of, we are going to have the weak acid solution. Weak acid which might be acetic acid, or it might be oxalic acid. So these we call it as the weak acid. Let us see how we perform the experiment. So this is the experimental setup what we are having. So this is the pH meter. So you can clearly see the pH meter here. pH meter which measures the pH of the solution, and we will be having a combined glass electrode. So a glass electrode combined with the reference mercury product, that is the calomel electrode. The electrode will be immersed in the solution. At present, we have only distilled water here. Now what we do, we are having a microburette to which we are going to fill the standard sodium hydroxide solution. We have the weak acid, and we have already prepared the standard sodium hydroxide solution. Now pipette out around 50 cm cube of this weak acid. What you have the weak acid, pipette out around 50 cm of weak acid and transfer it into the beaker. So this 50 cm cube, now it's placed under the stirrer for uniform distribution, and the glass electrode is immersed inside the solution to measure the pH. Now fill the microburette with the standard solution of sodium hydroxide. Sodium hydroxide. Once it is filled, place it back in the holder, and Now, before adding the sodium hydroxide first, initially note down the pH of this weak acid solution, which is approximately 3.65. Now, start adding sodium hydroxide in the increment of zero point 0.5 cm3, that is 0.5 ml. 0.5 ml. So for every addition of 0.5 ml, you have to note down the change in the pH happening. Now, the weak acid inside this is reacting with sodium hydroxide to give a salt and water. For example, if you are having acetic acid in our media, so acetic acid reacts with sodium hydroxide to provide sodium acetate as the salt and water. So now, for the increment of each 0.5 cm3, we are going to record the change in the pH until we are going to observe a sharp change in the pH. There should be a sharp change in the pH, means there should be a dramatic increase in the pH. Now you can observe the change in pH happening here. So which was somewhere around 5 is now increasing to 6.5, and this might go up to 8 or 9. The further addition has taken the pH to 9.3. So continue this addition of sodium hydroxide with increment of 0.5 ml until the pH reaches to 12. Later on add 2 or 3 trials. So already it has reached 12. So this will be sufficient. So once you reach the pH of 12, you can stop the titration. After completion of titration, so we have to do the calculation. For calculation part, here in this experiment we don't have any kind of calculation, only we need the graphical abstract what we are going to plot now. So initially record all the readings. We are having the volume of NaOH what we have added. So before adding an NaOH also we have to take the pH reading. Every addition of 0.5 ml has to take out the reading. And finally you have to plot a graph. There will be 2 graphs in this case. First we have to identify the Hopf equivalence point. So to identify the Hopf equivalence point, you have to plot a graph of the volume of sodium hydroxide along the x-axis and delta pH by delta V. When you say delta pH by delta V, it means that so delta pH will be the second value minus the first value. So the value which you obtained for 0.5 minus 0. So that will be the delta pH value, and delta V value will be the increment, that is the 0.5 ml. So after plotting this graph, you are going to get a parabolic graph here. So the point at which you are going to see a maximum increase in the pH will be the equivalence point of the solution. It will be the equivalence point of the solution. So by considering this equivalence point, note down this Hopf equivalence point of this. Note down the Hopf equivalence point, that is exactly half of this, and now plot a graph of volume of NaOH versus the pH directly. The volume of NaOH along the x-axis and pH along the y-axis. So by knowing the equivalence point divided by 2, so you are going to get the Hopf equivalence point. Note down the Hopf equivalence point, the volume consumed for the Hopf equivalence point here, and extrapolate the graph towards the y-axis. Extrapolate the graph towards the y-axis. So note down the Hopf equivalence point on the x-axis and extrapolate towards the y-axis. The value of pH what you get here will be the pKa of the solution. So note down the pKa and report it in the report. Thank you. Thank you for watching the video.